Hello everyone, this is Anil. In this video, we are going to derive convolution integral and impulse response related to basic control system theory. Okay, so I have taken here an arbitrary input u in t. The response to this arbitrary input y in t is known as convolution integral. While deriving this y in t, we take an delta in t. Okay, impulse input delta in t, or we also known as Dirac delta function. The response to this is known as h in t. Okay, this h in t is known as impulse response. So in this video, we are going in detailed derivation of convolution integral and impulse response. These things will be helpful someone who is preparing for semester exams. Okay, also who is preparing for IES, for them also this will be helpful for this derivation. So why we choose convolution integral? Generally, between input and output, the system J is represented in terms of ordinary differential equation. Okay, this is the generalized representation of ODE. Nth order derivative of y till y in t, and mth order derivative of u, and lower order derivatives u in t. And these are the coefficients a1, a2, so on up to an, b0, b1, so on up to bm. Okay, this differentiation is already linear. If we take this ai and bi, these coefficients are also constant, then we are dealing with LTI system. In basic block diagram representation of control system, we have input and output. In between, we have controller, actuator, and plant. And we represent everything in terms of ODE. Controller in terms of ODE, actuator in terms of ODE, plant in terms of ODE. Okay, system description by ODE. Then it becomes difficult to find out combined characteristics between input and output. So we for to reduce the complexity, we have chosen convolution integral. Okay. So one of the assumption we take here is that initial conditions are zero. Okay, if we take initial conditions zero, it is known as relaxed state. Before we derive the convolution integral, here introduce some of the theory. This theory will be helpful for derivation. Okay, so here what I have done here is that the arbitrary input unt is represented in terms of linear combination of standard input signal. This u1 and t, u2 of t, so on up to uk and t. These are the standard input signal and these are the coefficients. Why we have represented in this way? For this standard input signal, if you know the output y1 and t, y2 of t, so on up to yk of t, then this arbitrary input response y in t is represented in terms of c1 y1 and t, c2 y2 of t, so on up to ck yk and t. Okay, this is the main advantage if we represent arbitrary input in terms of standard input and signal. The same thing I have taken here, since we are dealing with the LTI system. I have taken here time shifted version of standard input signal. The same thing holds here for response y in t. Okay, so C1 y1 of t minus capital T, C2 y2 of t minus capital 2t, so on up to ck yk t minus capital Kt. Okay, now for deriving this convolution integral, the arbitrary input u in t I have approximated in terms of staircase approximation. Okay, so this u in t I represented in terms of staircase approximation u bar of t, the dependence on t. Okay, so we when we represent as a staircase approximation, we encounter these pulses p0, p1, p2, so on. Okay, so what we have done here is that the arbitrary input, okay, unity that we represent it as a u bar of t, and that is equal to summation of number of pulse signals. Okay, and if we take here in this u bar of t, if we take t tends to 0, when we take t tends to 0, then we get an u in t, and this u bar of t will have the amplitude of u of nt for this interval. Okay, and for pulse signal the amplitude will be same. Okay, in this interval the amplitude will be same, and the rest of the cases it will be 0. Okay, so these are the mathematical representation, and we need these definitions for deriving this convolution integral. Okay, so let me go to different slide. Okay, so for deriving this thing, we have introduced something known as unit pulse. Okay, unit pulse delta in t. So why unit means If you take here t, then we multiply here with 1 by t, so that the area will become 1. Area under the curve will be 1. That's why the word unit pulse. And how do we represent means? Mathematical means for t less than 0, t less than 0 it's 0. From 0 to capital T we have amplitude 1 over t, and t greater than capital T we have 0. Okay, so this is how we represent mathematically this unit pulse signal. Why we need this thing is, first we have represented arbitrary input in terms of pulse. This pulse signal we represent in terms of this unit pulse delta of t that depends on t in terms of this delayed version. Okay, using the shifted version of delta of t, we represent the pulse signal, okay, in terms of this delta of t. If you take here summation n goes from minus infinity to infinity, then we get this u bar of t that depends on t. This definition we already seen in previous slide. Okay, now if you know the response, right, for delta of t that depends on t, if you know the response h in t that depends on t, then the output for this input is y bar of t that depends on t equal to summation n goes from minus into infinity u of nt. For this delta of t, the response is h of t, okay, t minus n capital T into t. So what we have done basically an arbitrary input that we represent in terms of pulse signal. That pulse signal, okay, we represent it as a unit pulse, and we assume that we know the response for that unit pulse, and this is the expression we got. Okay, but our original signal is unt, right? So what we do here is that we take here t tending to 0. Okay, I represented here t tending to 0. When we take t tending to 0 of this unit pulse, we get delta in t. So when we take here t tending to 0, the amplitude will go to infinity. Okay, infinity. So this is how we represent it, and this is known as unit impulse, also known as Dirac delta function. Okay, Dirac delta function. So how do we represent it mathematical means? This is how we represent it. Delta in t equal to 0 for all t not equal to 0, and area, okay, minus into infinity delta into d tau, area equal to 1. So this is one of the definition for this Dirac delta function, also known as unit impulse function. So for this delta in t, we take the we assume that we know the response, and it is represented with h in t. Okay. This is the thing we already derived here. Y in t equal to y bar of t. We already, this is the expression we already got in previous slide. So what is u in t? U in t is that this u bar of t, we take t tending to 0. When we take limit t tending to 0, we get an u in t. The same thing applies here. For this u bar of t, this is the response y bar of t. Same by limit t tending to 0, when you apply, the response is known as y in t. For this input u in t, the response is y in t. The same limit t tending to 0 I have taken here. Okay. So when we take here limit t tending to 0, this n times capital T will become tau, and this t will become d tau. Okay, and this summation will become integration. So the final expression for y in t is, this summation will change to integration, nt will change to tau, and this h of t will change to h. Okay, this thing also we have seen in last slide, and t minus n capital T will change to tau, and t will change to d tau, and this response y in t is known as convolution integral. Okay, this is the thing we are discussing in this video, derivation of convolution integral. While deriving this convolution integral, okay, we have taken this delta in t, the response to this delta of t, h in t, that h in t is known as impulse response. Also, this convolution is also represented in this way. U in t, this is not multiplication, this is known as convolution. Okay, this is known as convolution. So u in t convolution h in t. So if we represent the system in terms of h in t, then this y in t equal to u in t, okay, convolution h in t. So if we have two systems in cascade and we represent in terms of impulse response h1 of t and h2 of t, so when we cascade this thing, then we get the response, we get the representation like h1 of t convolution h2 of t. How we got is, the output here is what, u of t convolution h1 of t. Again we have impulse response h2 of t, so we got impulse response, and for input to output, this is the relation we get here. The same thing I represented in terms of block diagram. Okay, so these things you can expect 1 mark questions in gate or in some competitive exams. Okay, thanks for listening. Thank you.